Yeah, that clock keeps ticking till we start up in here. Yeah, that clock keeps ticking till we start up in here. If you came to learn chemistry, you did your part. Time is ticking down, so just be ready, cause it's about to start. When we solving for problems, we solve it information. You know Ben's Chem videos will provide you with equations. Never have to stop and think about it, this the station that will provide you with the chemistry all in relation. If you came to learn chemistry, you did your part.
Hello. Oh, there we go. Hello, everyone, and welcome to the Ben's Chem Videos Sunday night live stream. Tonight, we are going to continue our discussion on thermodynamics, and I think that this is going to be the last thermodynamics live stream. It's possible that I might want to do another one next week where we do some practice problems. It's really all up to you guys. If you guys want to do another thermodynamics stream where we do a bunch of practice problems, let me know. I serve at the pleasure of my audience, and I'd be happy to do that if that's something that you guys want. Or maybe you want me to move on to another topic entirely. Again, I want to do whatever you guys want me to do. So all right, so that's it. So thermodynamics, without further ado, I present to you Thermodynamics Volume 6. As always, your feedback is more than welcome and highly encouraged, so please feel free to drop your thoughts in the chat if you're watching this live, and if you're watching this as a video, please feel free to leave me a comment below, because without your feedback, I am lost. Also, if you're watching this live, you can call into the show via Discord. We can have a nice voice-to-voice conversation. I think that'd be pretty cool. Discuss the content. So yeah, whatever you guys want to do. All right, so we're going to kick things off by reviewing the content from Volume 5, which is what we did a week ago. So Volume 5 was all about a property called the standard change in Gibbs free energy for a reaction, abbreviated by the symbol ΔGrxn with that little degree sign up there. So just to recap a couple things about Gibbs free energy, right? So Gibbs free energy is a very, very important and very, very useful thermodynamic property, because just like the entropy of the universe, Gibbs free energy is a criterion for spontaneity. But unlike the entropy of the universe, Gibbs free energy can be defined with respect to properties that are only defined relative to the system. So remember, the universe is composed of two components, the system and the surroundings. As you can imagine, measuring things for the surroundings can be pretty difficult and tricky to do. But with Gibbs free energy, we only have to measure things relative to the system, and so it's a very, very useful property. And so we know it's a criterion for spontaneity. We know it's related to the entropy of the universe, and we also know that a negative value of delta G indicates a spontaneous process. A positive value of delta G means it's non-spontaneous. And so the standard change in Gibbs free energy is simply the change in Gibbs free energy over the course of a chemical reaction such that the reactants and products are all in their standard states. So by now, we should know what a standard state is. If you don't, fear not, because I did define that very explicitly back in Volume 3 of this live stream series. By the way, if you want to watch any of the previous episodes in this live stream series, look no further than my Thermodynamics live streams playlist, which can be found in the form of link down below in the description. All right, so standard change in Gibbs free energy, reactants and products are in their standard states. We talked about three methods by which the standard change in Gibbs free energy can be calculated. I cleverly called them methods 1, 2, and 3. So method 1 was to calculate delta H for the reaction, the standard change in enthalpy for the reaction, and also delta S, the standard entropy change for the reaction, and then use the formula for delta G, which is delta G equals delta H minus T delta S. That's one method that you can use to calculate standard free energy change for a reaction. The second method is to calculate the standard delta G using tabulated standard free energies of formation for the reactants and products, and we saw a nifty formula that was that actually quite closely resembled the formula for calculating the standard change in entropy for a reaction from tabulated standard molar entropies. So that's method 2. And then finally, method 3 applies to stepwise reactions that can be expressed as the sum of a series of smaller reactions. So we talked all about that. We discussed these methods in detail, and we banged out a few problems where we got to put each one of these methods to work. Got a message from Bloodsport OSM, says hi. Hello, Bloodsport. Very happy to see you. Glad to have you with us, and that applies to all of you. Thank you very much for joining me. I hope this stream provides value to you, and I would also hope if it didn't that you would let me know. All right, so that was the content from Volume 5, so we're going to move on, talk about tonight's material. And so I want to start things off by talking more about Gibbs free energy, and I really think that by the end of this stream, we're going to have a much better understanding of Gibbs free energy and why it is so useful and so important in a practical sense. And I'm going to start it off by asking the question, why is it called free energy? What is so free about it, right? Is energy under any circumstances actually free? No, it's not. It's really not. Free energy would be a direct violation of the first law of thermodynamics. First law tells us that the total energy content of the universe is constant. You cannot create energy where there already wasn't energy from somewhere else. In other words, you can't add energy to anything without taking it from somewhere else. And so I apologize to all the Bernie bros that I'm about to offend, but healthcare is not free, college tuition is not free, and energy isn't free either. So the question is, why do they call it free energy? Well, I'm going to tell you. So free in this context means available to do work, right? So when we're talking about free energy, we're talking about the energy emitted by a reaction that is available to do work, okay? And so oftentimes we want to utilize the energy that is released by, say, an exothermic reaction to do work. And the classic example of this is the combustion reaction that takes place in an automobile engine. We want to harness as much of that energy that is released by that combustion reaction to do work and move our car forward, right? So to illustrate this concept, I'm going to show you this reaction here. So this reaction describes, let me move myself out of the way for a minute there. So this reaction describes the formation of ammonia, NH3. That's the stuff that you can find in your glass cleaning products, right? The stuff that gives that nice streak-free shine. I can't really do the noise. I was trying to do the, I can't do it. Anyway, so this is the formation of ammonia from nitrogen and hydrogen. So this is the balanced chemical equation for it. And the values of the standard enthalpy of reaction, the standard entropy change for the reaction, and the standard free energy change for this reaction are all shown here. So notice that the reaction is exothermic. It has a negative value of delta H under standard conditions. And notice also that the entropy decreases of this reaction, right? And remember, the entropy of the reaction, the delta ΔGrxn, that describes the system, not the universe, not the surroundings, but the system, right? So the entropy change for this reaction is negative. Nonetheless, this reaction is spontaneous. And we know it's spontaneous because the value of delta G carries a negative sign. But notice that the value of delta G, minus 53.00 kilojoules per mole, is less than the value of delta H, right? In other words, the amount of energy that is available to do work is less than the amount of energy that is released by this reaction. And so you might be asking yourself, well, why is that the case? And the reason is because some of the energy that is released by this reaction must go to increase the entropy of the surroundings by an amount that is large enough to make the entropy change of the universe positive, right? So I'll say that again. Some of the energy that is released by this reaction, some of this 91.8 kilojoules per mole that is released by this reaction must go to increase the entropy of the surroundings by an amount that is large enough such that the entropy of the universe increases and therefore gives us a spontaneous process. So again, delta G, what that represents is how much energy can be harnessed by this reaction in order to do work. Now, it's important to understand that delta G is a theoretical concept, right? If you were to run this reaction in real life, in a real laboratory using a real apparatus, you would not be able to use 53, you would not be able to you would not be able to do 53 joules or kilojoules of work from this reaction. And the reason why is because this is a theoretical limit, right? So a reaction that achieves the theoretical limit of Gibbs free energy is called a reversible reaction. And it's important to understand that reversible kind of has two meanings in chemistry. So back when we were talking about chemical equilibrium, a reversible reaction just means a reaction that can take place in either the forward or the reverse direction. That is not the same definition of reversible that we are talking about here. The definition of a reversible that we're talking about here is basically, like I said before, it's a reaction that achieves the theoretical limit of Gibbs free energy. And so to achieve that theoretical limit, what you have to do is you have to have a process that occurs in infinitesimally small increments. So you have to draw the energy out in infinitesimally small increments such that the amount of energy being drawn out exactly matches the amount of energy that is produced by that process. And so this is sort of like a little diagram of a process that is close to, but not quite reversible. So imagine you have like a pile of sand here that's on this piston here, and you have some reaction here that's producing some gas, it's building up pressure. And so you have the weight of sand that is almost identical to the pressure of the expanding gas. And imagine you just removed one little grain of sand at a time, right? So that the weight of that sand is just slightly, just infinitesimally less, just a tiny, tiny, tiny bit less than the pressure of that expanding gas. And so basically what you would have is a series of tiny, tiny, infinitesimally small expansions, right? Now, of course, this is impossible. All real reactions are irreversible, right? So some of that energy is going to be lost, inevitably lost to the surroundings as heat. So let me go over here for a second just to see if I can get your attention again. Sorry about that music. I don't know why. Okay, I just cut it off. So another example of reversible versus irreversible, and another thing that you might hear about in the context of thermodynamics is called nature's heat tax. So that basically just refers to the fact that you cannot run any real reaction in which you achieve the theoretical limit of Gibbs free energy. So the classic example of this would be like a rechargeable battery, right? So let's say you have a rechargeable battery, you charge that battery up to the point where it has a full charge, and let's say that that battery gets connected to a motor and it does 100 joules of work turning that motor around, right? And then it dies. Well, if you wanted to recharge that battery back to its initial state before it did those 100 joules of work, then it would require necessarily more than 100 joules of an energy input in order to charge that battery up. Why? Because some of that energy was lost as heat, right? If you wanted to retain all of that energy, you would have to have that process occurring infinitesimally slowly, which is not very practical at all, right? So nature takes a heat tax. Nature takes a cut of every energy transaction, right? All real reactions, all real thermodynamic processes are not reversible. They are irreversible. So let's go back to the PowerPoint. We're going to continue. So one thing that I want to talk about is delta G under non-standard conditions. So a week ago, we talked all about standard delta G. So let's talk about delta G under non-standard conditions, right? So consider the equilibrium that is shown by this equation here. So this describes the evaporation of liquid water into water vapor. And the standard Gibbs free energy change of this process is shown, coming in with a value of positive 8.59 kilojoules per mole, right? So under standard conditions, this process, liquid water evaporating, is not spontaneous, right? Because it has a positive value of delta G, right? But if you are in your kitchen and you spill some water on the floor, it evaporates spontaneously. Why? If delta G is positive, then why does that evaporation occur spontaneously when you spill water on your kitchen floor? Well, the answer is actually pretty simple. It's because ordinary conditions are not the same as standard conditions. And so if you have ordinary conditions or any non-standard conditions, then the value of the standard change in Gibbs free energy does not apply, okay? And so what I'm going to do is I'm going to take you guys to the whiteboard. So let me just get out of here for a second and let's see. Actually, before we go to the whiteboard, let's look at the formula. Sorry guys, I'm a little all over the place today. Let's see. All right, so we're going to take a look at the formula for how to calculate delta G for a reaction that is occurring under non-standard conditions, right? So the formula looks like this. So we have delta G. Notice that there's no degree sign over that delta G. It's just plain old delta G of the reaction is equal to the standard change in Gibbs free energy for that reaction plus this term over here, this RT ln of Q, right? And so the R, that is the gas constant reported in the appropriate units. In this case, the units of this gas constant are joules per mole per Kelvin. So it's 8.314 joules per mole per Kelvin, right? T, of course, is the temperature in kelvins, as it always is in any thermodynamic equation. T is for temperature. And then we have the natural log of Q. Now, Q is called the reaction quotient. Now, this is something that we defined fairly long ago when we were talking about chemical equilibrium. So I'm going to assume that you have somewhat of an understanding of chemical equilibrium going into this discussion. If you don't, have no fear, because I do have an entire playlist called Chemical Equilibrium's live streams, and I define the reaction quotient quite explicitly in within that playlist. So reaction quotient, so we're going to review that briefly here. So here we go. So here's the formula. Delta G is equal to standard delta G plus RT ln Q. So let's say you have a general reaction of the form A moles of A reacts with B moles of B to produce C moles of C and D moles of D. And it's a reversible reaction, not like a reversible thermodynamic process, but a reversible reaction in the sense that the products can react together to form reactants, and it's a dynamic process, right? And we're going to limit our discussion to gas phase reactions. So we're going to be talking about the reaction quotient with respect to pressure. So the reaction quotient is simply going to be the partial pressures of the products. So this P sub C, P sub D, those represent the partial pressures of those two products raised to the power of their stoichiometric coefficients, lowercase c and lowercase d, the product of that divided by the product of the partial pressures of the reactants A and B raised to the power of their stoichiometric coefficients, right? So that is the Q that you're taking the natural logarithm of within this equation here. Delta G is equal to standard delta G plus RT times the natural log of the reaction quotient. So now, I was getting a little bit ahead of myself earlier, but now we're going to go to the whiteboard and we're going to take a look at how this equation works and sort of why it works and why it makes sense. So, so here we go. So let me copy and paste the thing with the water, the liquid vapor equilibrium that we were looking at a moment ago. So let's see. Bear with me just a moment. Okay, back to the whiteboard. Okay, there it is. Okay. All right. So again, the formula, right, is delta G is equal to the, and that's Rxn, is equal to the standard delta G of the reaction plus RT, natural logarithm of Q, the reaction quotient, right? Now let's assume for the moment that we are operating under standard conditions, right? Standard conditions. I'll just put COND for short, right? So if we are at standard conditions, that means that the pressure of this water vapor here, in other words, I'll call that P sub H2O, right? The pressure of that water vapor is equal to 1 atmosphere, right? This is what a standard state of a gas is by definition, right? Standard state of a gas is a pure sample of that gas at a pressure of exactly 1 atmosphere. So, and if the pressure of this water vapor is 1 atmosphere, then also Q, the reaction quotient, is equal to 1. Why? Well, because again, the reaction quotient is the partial pressures of the products divided by the partial pressures of the reactants. But notice that the water on the reactant side of this equation is a liquid, right? And if there's anything that we can sort of dig back into our memory banks and remember about chemical equilibrium is that pure solids and pure liquids are always omitted from the equilibrium constant or the reaction quotient expression, right? Because their pressures, their concentrations, they do not change over the course of a reaction. This only applies to things that are in the gas phase, right? Okay, so we know that Q is 1, right? And so if we plug that into the equation here, we have the delta G is equal to the standard delta G, right? Which we know, right? That's given, 8.59 kilojoules per mole, plus RT times the natural logarithm of Q, which is 1, right? And the natural logarithm of 1, what is that? Well, natural logarithm of 1 is 0, right? And of course, anything times 0 is 0. So really, this entire term over here just cancels out completely, right? And so under standard conditions, delta G is equal to standard delta G, which is equal to positive 8.59 kilojoules per mole, right? So, okay, so we're starting to see now how this equation works and why it makes sense. Now let's talk about equilibrium conditions, right? So instead of standard conditions, let's talk about equilibrium conditions. So I'll just replace the word standard with equilibrium, right? Equilibrium conditions. So remember, chemical equilibrium, that basically just means that you are in the condition such that the rates of the forward and reverse reactions are equal, right? So let's see if we can, I'll probably need that for later, so I'll erase everything here. Okay. All right, so if we're at equilibrium conditions, well, the pressure of water under equilibrium conditions actually happens to be, now, and we're also going to assume, I forgot to mention this, but we're going to assume that we are at a temperature of 25.00 degrees Celsius, right? Because equilibrium constants, reaction quotients, they differ with regard to temperature, right? They're only constant at a constant temperature, right? So we're going to assume that this is the temperature we're working with because, well, 25 degrees Celsius is like the most commonly reported temperature in chemistry textbooks, right? So if you have equilibrium conditions, right, what's the partial pressure of water? Well, partial pressure of water under equilibrium conditions happens to be 0.0313 atmospheres, right? And again, there's no reason why you would necessarily know that. It's just a simple fact, right? It's just a relative to the nature of water, right? So at equilibrium conditions at 25 degrees Celsius, the pressure of that water vapor is going to be 0.0313 atmospheres. And so we see here that the pressure of the water vapor is much, much less than it is at standard conditions. So equilibrium conditions, definitely not the same thing as standard conditions, right? And for reasons that we discussed previously, the value of the reaction quotient is equal to, and in this case, not all cases, but in this case, it's equal to the pressure of that water vapor, which is 0.0313, right? And so if we plug that in to our expression, right, for this formula here, we get that the delta G for this reaction is equal to standard delta G, so that's positive 8.59 kilojoules per mole, right? 8.59 kilojoules per mole, plus the product of the gas constant, the temperature, and the natural logarithm of this reaction quotient. So what I'm going to do is I'm just going to take this, just to give myself a little bit more room. I am going to move that. Whoops. I'd like to move it. Sometimes my software doesn't really want to. Okay, there we go. I'm just going to move that down here just to get it out of the way to give myself some more room over here. Okay, so RT times natural logarithm of Q. So R, of course, that's 8.314 joules per mole per Kelvin, right? This is just something that you should probably commit to memory. It's a very, very important, very commonly used constant, right? Times the temperature. Remember, any thermodynamic equation, you must use absolute temperatures. So this 25 degrees Celsius, we must convert that into kelvins. It's an easy conversion. If you want to go from degrees Celsius to kelvins, all you have to do is add 273.15. And so 25 degrees Celsius becomes 298.15 kelvins, right? And then we take the natural logarithm of Q. In this case, Q is 0.0313, 0.0313, right? Now, if you plug this into your calculator, right, this expression right here, I'm going to highlight it. So this term here, 8.314 times 298.15 times the natural logarithm of 0.0313, right? If you plug that into your calculator, that is going to be minus, minus 8.59 times 10 to the third joules, right? So we have plus 8.59 kilojoules per mole, and that's joules per mole, right? So we have 8.59 kilojoules per mole minus 8.59 times 10 to the third joules per mole. Now, if we convert this value here of joules per mole into kilojoules per mole, then we simply get, it looks like I ran off the screen here, so let me fix that. There we go. So if we take this value and simply convert it to kilojoules, which is the unit that our standard delta G is reported in, right? That's going to be plus 8.59 kilojoules per mole minus 8.59 kilojoules per mole, right? Go ahead and bring that in there so it's nice and compact, right? So you have 8.59 minus 8.59, and so delta G for this reaction under equilibrium conditions is equal to 0, okay? Delta G is equal to 0 at equilibrium conditions. And that makes sense, right? Because that means that neither the forward direction of this process nor the reverse direction of this process are spontaneous, right? Those equilibrium pressures, those equilibrium concentrations are constant. Again, it is a dynamic process. It's not like there's no reaction occurring at all, but the reaction, the forward and the reverse reaction rates are equal, right? And so the concentrations remain constant. The partial pressures remain constant, right? And so now we have sort of a better understanding of how this equation works and why it is valid. So what I'm going to do is I'm going to grab a problem real quick in which we find the delta G of a reaction taking place at non-standard conditions, and we use this formula in order to solve the problem. So let's see, I might need to make this a little smaller to make sure I have enough room here. Okay, so here's the problem. It says to consider the following reaction where we have CO2, carbon dioxide, plus carbon tetrachloride, CCl4, reacting to produce 2 moles of COCl2. COCl2, that actually goes by the name phosgene. It's a very, very poisonous gas. It was actually used as a weapon in World War I, killed tens of thousands of people. Pretty tragic, but anyway. So what we're doing is we're going to calculate delta G for this reaction at 25 degrees Celsius under the following conditions. And those conditions are that the partial pressure of CO2 is 0.112 atmospheres, partial pressure of carbon tetrachloride is 0.174 atmospheres, and the partial pressure of phosgene is 0.744 atmospheres, okay? So again, the formula that we are going to be using is the one that we just previously looked at, which is that delta G for this reaction is going to be equal to the standard delta G for this reaction plus RT ln of Q, the reaction quotient, right? So we need to figure all these things out. So this is actually going to be a pretty lengthy problem, I think. So let's strap in. And by the way, anybody who may be following along, if you'd like to follow along, use your scientific calculator to follow along with me. I would wholeheartedly appreciate it, because it is entirely possible that I make a mistake. In last live stream, I actually did make a mistake. Somebody caught me, and I was very, very thankful and grateful that somebody caught me. I made a little calculation error. So, all right. So let's start by finding the standard delta G for this reaction. How do we do that? Well, this is something that we talked about in the last live stream. The method that I'm going to use to find the standard delta G for this reaction is I'm going to use tabulated standard free energies of formation, right? Tabulated standard free energies of formation. And so I'm just going to look them up in my chemistry textbook. Well, to be fair, I've already looked them up. I wrote them down just so I could be nice and prepared for my live stream here. So what I'm going to do is I'm just going to make a little table here. I'll make it off to the side over here. So I have, let's see, I have the standard Gibbs free energy of formation, right? And I have 3 compounds, right? I've got CO2, which is a gas. I've got carbon tetrachloride, which is also a gas. And I've got phosgene, COCl2, which is a gas. And let me pull this whole thing to the left just for a moment so that I can include the units. Units are very, very important. Always have trouble pulling things around. There we go. Okay, so the unit of standard free energy of formation, that's kilojoules per mole. And again, I just found these in my chemistry textbook. So somewhere in the back of your chemistry textbook, there's an appendix. In that appendix, there's a table. And in that table, there are tabulated standard free energies of formation. So for CO2, the value that I found was minus 394.4 kilojoules per mole. For the carbon tetrachloride, it's minus 62.3 kilojoules per mole. And for phosgene, it's minus 204.9 kilojoules per mole, right? So again, we're going to use these tabulated standard free energies of formation to get the standard delta G for this reaction, and that'll take care of this term within this larger equation here, right? So remember, the formula for finding the standard free energy change for a reaction using tabulated standard free energies of formation is to take the sum of the free energies of formation of the products minus the sum of the free energies of formation for the reactants, everything multiplied by its stoichiometric coefficient, right? So we're going to take the products, right? So the coefficient in front of that phosgene is 2, so that's going to be 2 times the standard free energy of formation of phosgene, which is the minus 204.9 kilojoules per mole, right? And I'm going to subtract from that minus the sum of the standard free energies of formation of CO2 and carbon tetrachloride multiplied by their coefficients. Luckily, the coefficients in front of these are 1, so I can sort of skip that step, right? So it's going to be minus the sum of negative 394.4 plus negative 62.3. And let me back up a little bit here. I forgot to put my units in. So that's kilojoules per mole and minus 62.3 kilojoules per mole, right? So this whole expression here, right? 2 times minus 204.9 minus the quantity of negative 394.4 plus negative 62.3. That's going to give us this standard delta G for this reaction. So I actually haven't solved this problem yet. I just kind of put it up here. So bear with me while I solve it. And again, this is a good opportunity for anybody who's following along to also try to solve this and see if you got the same thing that I got. Because if we get something different, then one of us did something wrong. And I hope that wasn't me. All right, so 2 times 204.9. Excuse me. Minus negative 394.4, 62.3. Okay. All right. The value that I got for this whole thing, and I'm going to just erase all this calculation stuff just to make sure I don't run out of room here. The value that I got was positive 46.9 kilojoules per mole. Okay, so we've taken care of this term right here, this standard delta G for the reaction, right? R, that's easy, that's just the gas constant. T, 25 degrees Celsius, so in other words, 298 Kelvin. But Q, right? Q, that's the reaction quotient. That's going to take a little bit of work to find, right? Because we're given the partial pressures of both the reactants and of the product. So we have to use those partial pressures in order to calculate the reaction quotient. So I'll do the calculation for Q down here, right? So Q, again, that's going to be the partial pressures of the products raised to the power of their coefficients divided by the partial pressures of the reactants raised to their coefficients. And so I'll put my fraction bar in there. So the partial pressure of this phosgene here is 0.744 atmospheres, so 0.744, right? And that's going to be squared because its coefficient is 2, so we're going to raise it to the power of 2. And we're going to divide that by the product of the partial pressures of CO2 and carbon tetrachloride. So for CO2, it's 0.112. For carbon tetrachloride, it's 0.174, right? And both of the coefficients are 1, and so we raise them to the power of 1, which means we just kind of leave them alone, right? So let me calculate this one again. Anybody watching would like to calculate this, I would sure appreciate it. So we have 0.744 squared divided by the product of 0.112 and 0.174. All right, so the value for the reaction quotient that I got, go ahead and keep this to 3 significant figures, is 28.4. 28.4. Okay, so that takes care of our Q, right? So basically we have everything that we need now. We can plug these into the formula and solve away, right? So let's see, I'm just going to take this whole mess right here and move it as far to the left as I can. It looks okay. It looks like my Kelvin over here didn't, or not my Kelvin, but my little K for kilo. Let me write that in again. So this is kilojoules per mole, right? Okay, so we're finally in a position where we can calculate delta G for this reaction, right? So it's going to be equal to, I'll go back to my purple color here. It's going to be equal to the standard delta G. So the standard delta G in this case, we just calculated it a few moments ago. That's 46.9 kilojoules per mole, right? And we're going to add that to the product of R, T, and natural log of Q, right? So R, 8.314 joules per mole per Kelvin, right? T, the temperature, that's 298 kelvins. How did I get that? Well, 25 degrees Celsius you add 273 degrees to it. That's how you convert from degrees Celsius to kelvins, and so that becomes 298 kelvins. Let me go ahead and drag this whole thing over a little bit to the left so I can try to get some room here. Okay. I don't know why that happened, but let's see if I can zoom back in. Accidentally zoomed out there. Actually, might be good for me to zoom out a little bit, give myself a little bit more room. There we go. Okay, so we have R, 8.314 joules per mole per Kelvin. T, the temperature, 298 kelvins. And then we have the natural logarithm of the reaction quotient. So the natural logarithm of 28.4, right? Okay, so we got a lot of calculating to do. So it's going to be 46.9 kilojoules per mole plus this whole thing here. So let me calculate that real quick. So that's 8.314 times 298 times natural log of 28.4. And the value that I got, put this in scientific notation, is 8.29 times 10 to the third. And that is joules per mole, right? Joules per mole, right? Because the kelvins cancel out, right? Kelvin cancels with Kelvin, so we're left with joules per mole. Okay, so if we take this 8.29 times 10 to the 3 joules per mole, and we do a little quick conversion where we convert that to kilojoules per mole, that's going to become simply 8.29 kilojoules per mole. So let's go ahead and just do that quick conversion. So it's 8.29 kilojoules per mole. I'll go ahead and lasso this up to move it a little closer. Okay, so we have 46.9 kilojoules per mole plus 8.29 kilojoules per mole. So 8.29 plus 46.9, and taken to one decimal place, going to be 55.2 kilojoules per mole. And that's positive, right? Positive 55.2 kilojoules per mole, which means that under these conditions, the forward reaction, the reaction of CO2 and carbon tetrachloride becoming phosgene, is not spontaneous. The reverse reaction, where the 2 moles of phosgene decompose into CO2 and carbon tetrachloride, that is spontaneous under these conditions, right? Okay, so there's delta G applied to non-standard conditions. I certainly hope that that was helpful. So the last little thing that I'm going to show you guys is the relationship between standard Gibbs free energy change for a reaction and the equilibrium constant, right? So we're looking at the relationship between standard delta G for a reaction and K, right? The equilibrium constant. So again, this kind of requires us to dig back into our memory banks back when we were studying chemical equilibrium. Like I said, if you're kind of fuzzy on equilibrium, I have a whole playlist talking about it, so you're more than welcome to check that out, and I can link that in the description if you're interested. So if we write that formula down again, leave it to me to erase it shortly before I need it. But if we write down that formula for non-standard conditions, what is it? It's delta G, right, for the reaction is equal to the standard delta G for the reaction plus RT ln of Q, the reaction quotient, right? And so K, the equilibrium constant, carries the same expression as Q, the reaction quotient, right? Where you have products raised to their coefficients divided by reactants raised to their coefficients. The only difference is that K, the equilibrium constant, is strictly under the equilibrium condition, the condition in which the rate of the forward reaction is equal to the rate of the reverse reaction, right? And so if we are at equilibrium, then this Q essentially becomes a K, right? Because we're talking about the equilibrium constant here, which is equal to the reaction quotient under the conditions of chemical equilibrium. We also know, because we saw a few moments ago, that in an equilibrium, right, the rate of the forward and reverse reactions are the same, which means the reaction is not spontaneous in either direction, which means the non-standard delta G of the reaction is 0. So I'll go ahead and replace that. I'll set that equal to 0. And so we arrive at this equation here. 0 is equal to standard delta G for the reaction plus RT times the natural logarithm of the equilibrium constant. And so if we rearrange this a little bit, we get, I'm just going to subtract delta G from both sides of this equation, right? So we have minus delta G for this reaction under standard conditions is equal to RT ln K, right? And then finally, if we multiply this whole equation by -1, we get that the standard Gibbs free energy change for the reaction is equal to minus RT ln of K, right? So this is an important equation, right? This is how we relate the equilibrium constant of a reaction to the standard change in Gibbs free energy for a reaction. And so if you remember back when we were talking about equilibrium, it kind of makes sense that standard Gibbs free energy and equilibrium constant are related, because the equilibrium constant is itself kind of like an expression of spontaneity, right? It tells you how far a reaction proceeds, either in the product or the reaction direction under conditions of equilibrium, right? If that equilibrium constant carries a very, very large value, that means the concentrations of your products are very, very high at equilibrium. On the flip side, if your equilibrium constant has a very, very small value, that means the concentration of those reactants are very, very high at equilibrium. And so we're going to look at a couple of situations here just to better understand this relationship between delta G under standard conditions and the equilibrium constant. Got a couple of message in the chat. One from Aaron. It says, "Hi, huge fan. I was the kid on Omegle that you met." Oh, cool, man. Happy to see you here. Thanks for coming. I can't remember which one you were, but it's good to have you here. And I hope you enjoyed that video. All right. So I'm going to take this whole thing and just kind of move it up here to use that as a reference. And so let's talk about a situation in which the equilibrium constant is less than 1, right? We have a small equilibrium constant, right? So if the equilibrium constant is less than 1, what does that mean? Well, that means we're going to be taking the natural logarithm of a number that is less than 1, right? And if you have the natural logarithm of a number that is less than 1, then that means it is going to carry a negative value. So if K is less than 1, then the natural logarithm of K is going to be less than 0. In other words, it's going to be negative, right? If K is less than 1, then the natural logarithm of K is going to be negative. And I would encourage you to try it, right? Like go into your calculator and just take the natural logarithm of like 0.3 or something like that. It's going to be a negative number, I promise you, right? And so since the natural logarithm of K ends up being a negative value, when you apply it to this entire term over here, this minus RT ln K, then that means that the delta G value becomes positive. It becomes greater than 0, right? And so again, if K is less than 1, that means delta G is positive. And if delta G is positive, that means that the forward reaction, so let's just denote that by saying just a simple equilibrium. Like, so if we have like let's see, not delta. Let's say if we have like A reacting to form B, right? And so imagine that the forward reaction is A becoming B, and the reverse reaction is B becoming A, right? If that's your chemical equation, right, and you have a situation where K is less than 1, natural logarithm of K becomes negative, which means overall your standard delta G becomes positive. That means that under standard conditions, you have a non-spontaneous reaction in the forward direction and a spontaneous reaction in the reverse direction. Aaron says, oh yeah, what's the Omegle video called? Oh, it's just called like sulfur hexafluoride Omegle or something like that. I can, if you send me a DM on Discord or something like that, you can join my Discord server. You can find me that way, and I can send you a link to it if you want to see it. So, all right. I'm glad to hear you're a fan. Okay, so that's basically if you have a small equilibrium constant, right? If you have a small equilibrium constant, that means that the reactants are favored at equilibrium, which means the reverse reaction is preferred, so to speak. The reverse reaction is going to be spontaneous under standard conditions, right? Now imagine that the opposite is the case. Now imagine, I'll just erase all of this. Imagine that the equilibrium constant is greater than 1. Whoop, not greater than 0. Imagine that the equilibrium constant is greater than 1. Well, if the equilibrium constant is greater than 1, then that means that the natural logarithm of the equilibrium constant is going to be greater than 0, right? It's going to be positive, right? And if natural log of K is positive, then that means that this minus RT ln K term is going to be negative, which means that the standard delta G for this reaction is going to be negative. It's going to be less than 0, right? And so negative delta G, that means spontaneous. And so under these conditions, right, under standard conditions, if you have a product favored equilibrium, in other words, you have a equilibrium constant greater than 1, you can easily predict here that the forward reaction is spontaneous and the reverse reaction is non-spontaneous. And so this just kind of shows us, right, how the equilibrium constant and the standard delta G for a reaction are related. Now imagine the following situation. We're going to do one more here. So imagine the situation in which K is equal to 1, right? This would describe a reaction that proceeds exactly halfway. So this would describe a reaction in which the concentration of the reactant and the product are equal at equilibrium. Well, what would that look like, right? Well, if K is equal to 1, then the natural logarithm of K is going to be the natural logarithm of 1, which is 0, right? And if this term over here, this ln K is 0, then this minus RT ln K, that whole thing also becomes 0. And so therefore, the standard delta G for this reaction is equal to 0. So this is just kind of a sort of coincidence in which standard conditions for this type of reaction they happen to be identical to equilibrium conditions for this particular reaction. And so that is the relationship between the equilibrium constant and the standard change in free energy for a reaction. It's all related. So, all right, everybody, that is going to do it. So that is it for thermodynamics. Like I said at the beginning of this stream, if you are interested in perhaps doing some more practice problems next week, I'd be happy to do that. It all just depends on whether people are interested in it or not. Or if you would like me to cover a different topic entirely, I'm happy to do that too. Just all depends on what you guys want. So it's been very, very fun covering this topic. It's a very, very cool topic because I think this is one of the things I said in volume 1 is because studying thermodynamics gives us the opportunity to address the question, why? Why do physical and chemical changes occur in the first place? And so I hope that if you've been following this live stream series from beginning to end, as I hope you have been, that you have gotten a little bit more insight as to why physical and chemical changes occur. It's all about the entropy and the Gibbs free energy. So thank you very much for watching. I look forward to bringing you more content in the very, very near future, and I will see you soon. So stay tuned. Take care.